Hi everyone, it's Alyssa, and we are live here with our cram session. It's going to be the algebra cram session, and live from my clearly not a professional studio room, but here we are. And any questions that you have, please put them in the comment section and write question before it, and so that I can really see it quite easily. But what I'm going to do is, my plan today is to go through all of the biggest issues, sort of problem areas that students in algebra seem to have. I'm going to cover as many topics as I can in the next hour or two. And yeah, of course, any questions that you have, please put them in the comment section there, and so I can answer those. Anything algebra related, put it in there. Absolutely, we're going to cover it. Right. So I am going to get started here. I'm going to put my my handy dandy whiteboard here so I can start. Oh, come on. This worked perfectly beforehand. Why does everything work less well when we're going live on things? It's just the way it is. That's the way life is. And I do apologize. I have a little bit of a cough left. I had COVID a few weeks ago, and I can edit those out of the pre-recorded videos, but not so much of the live ones. So, all right, let me get the whiteboard here. And yeah, here we go. There we are. All right, so here's our whiteboard. And I am going to start right off the bat, linear equations. Those are sort of the bread and butter when we first start out of algebra. Again, as I said, any questions you have, drop them in the comments. Just put question before that so I can spot them very easily. Right, so I'm just going to start here with linear equations. One of the major things that we need to work with when we're talking about algebra are linear equations. And that was a horribly drawn XY axis, wasn't it? Oh, yes, it was. Let's make this presentable. There we go. Right. So linear equations are often, most commonly, presented in y equals mx plus b, or slope-intercept form. We say it's slope-intercept because the two constants here, the m and the b, represent the slope and the y-intercept of the line. And that makes them really easy to graph. It's a really nice format if we're wanting to graph these lines by hand. Of course, if we have a graphing calculator, that's easy peasy. We just type it in, we see the graph, boom, there we got it. But if we're doing this by hand, and a lot of times on algebra exams, on tests, and also like on the SAT and PSAT, there will be things where it's advantageous to be able to do it by hand. So for slope-intercept form of the line, slope here, you might see it called change in y and change in x, or rise over run. And rise over run, this talks about how much we're going up or down. That's our rise. And run is how far we're going left or right. So we have here rise over run. So if I had a line that was, go away, select again for more options. You annoy me. There we go. If I had a line that was, say, y equals 2x plus 5. There are 2 there. It's not in a fraction form. So what is it? Rise over run? This isn't a fraction. But we can put it in a fraction. We can change it to 2 over 1. Rise over run. So it's going to be going up 2 towards the positive up here, positive y. And it's going to be running to the right 1 towards the positive. We have our positive and negative there. So this line here, y equals 2x plus 5. Our slope is 2, or 2 over 1. Our y-intercept is 5. So we're going to go up 1, 2, 3, 4, 5. And then my slope is 2 over 1. So I'm going up 2 and to the right 1. So I go up 2 and to the right 1. And for a line, honestly, that's all you need is just 2 lines. 2 dots, excuse me. And then you can draw your line. And we can have this poorly drawn, approximately like this line. And that's why this slope-intercept form is so great. The standard form of a line also shows up, and standard form is when you have ax plus by equals c. A lot of times I think teachers like to present it that way, just kind of mess with you a little bit. But when it's in that format, you can choose to convert it into slope-intercept form to make it easier to graph, or you can put it in a graphing calculator, or you can make an XY chart where you put in some values for X, solve for Y, and then you can have a chart. Slope-intercept's the way to go, but sometimes you will see these on math exams, algebra final exams. Yes. Any particular questions you have, pop them in the chat, put question at the beginning, and I will do my best to answer everybody's questions. Okay, another common one. Again, I'm just going down the list of things that are common questions that students have for algebra. Inequalities. Oh, inequalities are a big one. The two most common kinds that we have for inequalities are ones that are, say, a single variable, like 2x plus 3 is greater than 10. And then we have the double variables where we have an x and a y. But let's start with the single first. So first we have 2x plus 3 is greater than 10. You're going to solve this almost identically to if it were an equals. If it were 2x plus 3 equals 10. There's one little thing you have to be wary of, which I'll get to in a second. So here, 2x plus 3 is greater than 10. We always want to undo what's been done. So we've got our x here. What's been done to x? It's been multiplied by 2, and then 3 got added. So we undo that in reverse order. So first we're going to undo that adding 3. Do the opposite of that, subtracting 3. And we do it to both sides to keep things fair and balanced. So on the left, I'll now have 2x, and it's greater than 10 minus 3, or 7. And now x has been multiplied by 2, so we need to undo that. Divide by 2. Divide both sides by 2. And we get x is greater than 7 halves. Like, hey, that's exactly the same as if it was an equal sign, right? Almost. And here is the thing that makes it different and that can really mess you up if you forget it. All right, let's try this again. Put a little negative there in front of the 2. Let's try this again. Same sort of beginning. Like, okay, let's undo that, adding 3. Let's subtract 3 from both sides. Now I've got that negative 2x on the left, 10 minus 3, or 7 on the right. And then I'm going to divide by negative 2, and I divide both sides by negative 2. And then I've got my answer that x is greater than negative 7 halves. Is that right? No, it is not. Oh no, what happened? What happened is anytime you multiply or divide by a negative when there is an inequality in the mix, a greater than, a less than, a greater than or equal to, a less than or equal to, you have to flip the sign. No ifs, ands, or buts. This sign right here, you have to flip it. If you do not flip it, it will be wrong. At this stage in the game, when we're prepping for SAT or for a final exam, I don't think it's as important to understand necessarily why this is the case. If you are interested, I do have videos on that explain that more in depth. But honestly, if you're prepping for an exam right now, just memorize this rule. That when you have that negative, you have to flip the sign if you are dividing or multiplying by a negative. Now, you may be asked to graph your answer on a number line. So I have our number line here. Number lines, the one thing to remember about when you're graphing inequalities is the difference between an open circle and a closed circle. Open circle, you're going to use when it's a less than or a greater than. Closed, you're going to use with less than or equal to or greater than or equal to. Because the open circle means it does not include that number. The closed circle means it does include that number. So here, less than negative 7 halves. And I did not draw this to scale. So I'm going to say if that's 1, 2, 3, these are negatives. 1, 2, 3. So negative 1, negative 2, negative 3, negative 4, 1, 2, 3. Okay. So negative 7 halves or negative 3.5. So it's going to be around here, but because it's less than, I need to make it an open circle. And then I want to shade in the numbers that are less than. because it doesn't include -7/2. It goes right up to it, but it doesn't include it. If this had been less than or equal to, then you shade that in. Right. Again, any questions you have, pop them in the comments, put question at the front. I will absolutely cover them. They can be specific or general, like a topic you want to cover or a specific problem you have issues with. We will cover it. Okay, inequalities that are with two variables. So let's say we had, there's a good one. Let's see, 3x plus 4y is greater than or equal to 8. For me, if you're graphing this by hand, the easiest way is to get it into the inequality version of slope-intercept form. We get y by itself, we get everything else on the right, and that's how we're going to do this. That's how I'm going to do this. Again, we're assuming we have to do this manually. We're not, we're not doing the graphing calculator way. Right, so I want to get everything on the right except for the y. So I got ahead of myself there. I'm going to subtract that 3x from both sides because 3x is being added to the 4y. So I want to undo that. I get 4y is greater than or equal to a -3x plus 8. And then y is being multiplied by 4. So I need to undo that. So I'm going to divide everything by 4. Actually, I want to split that up, make it a little easier to look at. There we go. I get that y is greater than or equal to -3/4 x plus 8 divided by 4 is 2. Right, and I didn't divide or multiply by a negative, so everything's good. I didn't have to flip the sign. Now, when you graph this, you graph it very similarly to graphing just a straight, I can't draw a straight line here to save my life. There we go. We're going to do this very similarly to when we are graphing just regular lines that are slope-intercept, but that little greater than makes it slightly different. We do the same beginning process. We have our y-intercept there is 2, a little 2. And I've got my slope is -3/4, so -3 over +4 is how I'm going to choose to look at that. So I'm drawing it. I go down 3, 1, 2, 3, and I go to the right 4, 1, 2, 3, 4. So there's my second point there. That's close. It's not the most perfect line I've ever drawn. I'm trying to get through those two lines. Let's see. Do it like that. There you go. That's not too bad. All right. Now notice I did draw this as a solid line because it is greater than or equal to. If it had been just a greater than or less than, it would have been a dashed line because it would not be including the line. That's what that or equals to or equal to signifies there. Now we have one last thing that we have to do to make this our correct answer, and that is we have to shade. The easiest way to do this, to figure out where we should shade, because we want all the answers that would make this true, all the x's and y's that would make this true. It's not just one little line of answers like with a plain line that's just an equals. No, because this is a greater than or equal to, we got to shade. Pick a point. If 0, 0 is not on the line, that's a good place to start. It has to be not on the line. So 0, 0, and you plug it in to this equation. So plug in a 0 for x and a 0 for y. 0 is greater than or equal to -3/4 times 0 is just 0. 0 plus 2 is 0 greater than or equal to 0 plus 2. Is that a true statement? No, that is not. 0 is not greater than 2. So you shade where it's true. Here, the 0, 0, that's the false area. So this part over here where 0, 0 is the false area. You shade the other side. This is going to come back when we talk in a little bit about inequalities that are, or shading parabolas, quadratics, when we're shading those. We have those inequality signs in the quadratics. This test, taking a test point and then shading it, is going to come back. All right. Again, if you have any questions, if there's a topic you want to cover specifically, I am just going down the list of major topics in algebra that students have problems with and difficulties with that I've found. But anything you want to go over, pop it in as a comment, put a question, put the word question in front, and I will definitely cover it. Oh, okay. Here's one. Division with polynomials. Oh my goodness. It's not one a lot of people like, but it comes up a lot. There's two forms of division with polynomials. These are long division and synthetic division. Long division, no one likes this. No one likes polynomial long division. I don't even think the teachers like it. That's my story. I'm sticking to it. Synthetic division, piece of cake, but they are never going to tell you synthetic division before long division because they know how much easier it is and that you won't be willing to do the long division after you learn synthetic. Okay. When you are doing long division with a polynomial, it's all about being very methodical, very careful, and very precise. And it's going to take a minute. Just be prepared. So let's say I want to divide x plus 1 into 5x cubed plus 2x squared plus 3x minus 6. No clue how this is going to turn out. We'll see. We'll discover together. Okay, the key to these, you look at just this x. Do not worry about anything that's attached to it. It's just going to come along for the ride. You look at the first term that's here, and you say x times what equals this term, whatever it is. So here it's x times 5x squared equals 5x cubed. That's what you're asking in your head. What x times what equals 5x cubed? So okay, so it goes in there 5x squared times. I'm writing it right above the squared to keep things nice and cohesive. And then you multiply back, but you multiply it by everything. And then you're going to write it all down here. So 5x squared times x goes here. 5x cubed. 5x squared times 1 goes here. 5x squared. Now this, what we're about to do right here is the one thing that, oh my goodness, it trips students up all the time. I totally understand it, but just I'm warning you, this is the key. You're going to subtract. You're subtracting everything. Be super careful with that. So you're subtracting first the 5x cubed, and then you're subtracting the positive 5x squared. So 5x cubed minus 5x cubed is 0. Those cancel. They better cancel. If they don't cancel, we did something wrong when we wrote this number up here. Right, then 2x squared minus a positive 5x squared is negative 3x squared. And we bring down the next term. Then you repeat. Like I said, this is methodical. You have to be methodical and careful, and it is tedious. It just is. That's all there is to it. All right, so x times what equals negative 3x squared? Negative 3x. And then we do the same thing we just did. We multiply it by that whole x plus 1, and we write it down there. Negative 3x times x is negative 3x squared. Negative 3x times 1 is negative 3x. And I'm going to subtract all of that. Again, that's the part that's going to throw people. It throws people all the time. Totally understandable. I'm not casting shade at anyone. I'm just saying facts. Like this happens. Everyone makes mistakes here. You're subtracting this whole thing. So negative 3x squared minus a negative 3x squared is 0. Then 3x minus a negative or plus a positive 3x is 6x. I bring down my last term. Okay, then x times what equals 6x? Positive 6. Okay, same thing. Multiply back, put it down here. I erase my 6. Okay, so 6 times x is 6x. 6 times 1 is 6. And we're subtracting this whole thing. 6x minus 6x is 0. It better be 0. And negative 6 minus a positive 6 is a negative 12. And that is my remainder. remainder is negative 12. So all that mess, it's so easy to make a simple mistake somewhere along the way and get it wrong. I get it. So be very careful, be very methodical. And it's that minus when you're subtracting, make sure you're subtracting everything. Be very careful with that. If you want to change all the signs, like say here, you want to change this to plus, minus, minus like that. Sometimes that makes it easier. It does for me. Now let's try this same problem using synthetic division, and you'll see why this is so much easier. For synthetic division, you just have this little bar like that. You take what you're dividing into, and you're going to write all those coefficients on the top. If there's any x that's missing, like if you had an x cubed and an x squared, but no regular x, and then you had a constant, you're going to put a 0 in for any missing. But here there's none missing. We have an x cubed coefficient that's 5, an x squared coefficient is 2, an x coefficient is 3, and a constant is negative 6. Then you look at what you're dividing into it, x plus 1. For the purposes of most algebra classes, they're not going to give you something other than a plain x and then a number. It's possible if you have that situation in your class where they're asking you to divide by like 2x plus 3 or something, let me know and I'll go over that. But x plus 1, x plus 5, x plus 7, those kind of single x's and then a number is the most common. In that case, what you do is you take this plus 1, and this number, this constant, you do the opposite. So here it's plus 1, you're going to write negative 1. Honestly, that is the hardest part of this synthetic division process. It's the part that you may forget easily. The rest of this is going to be a cakewalk. And what you do, bring down the first number, then you multiply. Negative 1 times 5 is negative 5, and you write it right here. Then you add. 2 plus negative 5 is negative 3. Then we repeat. Negative 1 times negative 3 is positive 3. Then we add. 3 plus 3 is 6. Negative 1 times 6 is, I put it there, negative 6. We add negative 12, and that's my remainder. And what are these? Those are my coefficients for my answer. 5x squared, you always start one exponent lower than the original, minus 3x plus 6, remainder of negative 12. Oh my goodness, wasn't that so much easier? So much easier. But as is often the case in a math class, you often will be required to write this whole long thing out. Yeah, that's life sometimes. We have to do it the long way and prove that we can do it the long way. And then we get to do it the much shorter, easier way. So, that's it. Oh, thank you, Harleen. That's nice of you to say. That's a nice little comment there. Thank you. So, yeah, if anybody has, if you're just new, just hopping on, if anyone has any questions, just type in question in the comment box, and I will cover that. Again, I'm just going down the list of things that are covered in algebra that students often have difficulties with. Okay, let's see. Oh, quadratics. There's so much in quadratics. I'm weird. I like quadratics. Okay, quadratics are our parabolas. So, wow, that's a bad drawing of a parabola, isn't it? That's slightly better. Slightly better. Thank you. Yes, I do like smiling. It's more fun in life when we smile a lot, isn't it? Always cheers me up. All right. So, okay, here is our parabola, our basic parabola of y equals x squared. So many things that we can do with parabolas, and so much we are asked to do with parabolas when we are in algebra. Okay. I'm going to start with one that is really easy to do, but I think a lot of students forget it, but it comes in handy really often. And it's this little formula right here. Why am I covering this even when it's not? You'll see in a second. It is x equals negative b over 2a. What do we mean when we say a and b? This is referring to our little y equals ax squared plus bx plus c. It sometimes can be 0. It just depends if we are graphing or if we're solving for x. Both of these versions are very common. Okay, so it's the coefficient of the x squared. That's our a. The coefficient of the x is our b. So what is this? This x equals negative b over 2a. This is our formula for the axis of symmetry. I don't know why I think it sounds cool. Just the axis of symmetry. Sometimes things just strike you and you go like, just kind of a cool sounding name. The axis of symmetry is the line that you can draw, if you can draw lines, unlike me, that goes straight through a parabola and divides it into two congruent symmetrical parts. They are reflections. Congruent reflections, they are symmetrical. Is the axis of symmetry. And it goes right through the vertex. So finding this axis of symmetry gives us the vertex. We know the x value for the vertex. That can be so helpful. A lot of times we're asked to find the minimum or the maximum, or what's the x value at the minimum, or what's the x value at the maximum. That's it. That's all you need is x equals negative b over 2a. And you're done. You don't have to graph it. You don't have to do anything crazy. No. So I'll give you an example of that. So if I had, let's say, y equals 5x squared minus 3x plus 7. And they say, what is the x value of the vertex? And the x value of the minimum or max, this would be a minimum because it's opening up. The x value of the minimum. This is it. Negative b over 2a. So negative here means the opposite of. So b here is negative 3. The opposite of that is positive 3. And then 2 times my a, 2 times 5, or 10. So there we go. This particular parabola, if we are to graph it, has a vertex where x is 3/10. The axis of symmetry goes through 3/10. Excuse me. And then if we needed to find out the y value for that vertex, we could plug 3/10 back in here and solve for y. So this is a really, straightforward sort of equation. There's not a lot to it, but my goodness, does it come in handy, especially if you're studying for the SAT and PSAT all the time. Axis of symmetry. Okay. Another thing that happens all the time with quadratics is factoring. The main areas of factoring are ones like we have, let's see, that's not y equals, shame on me. It is 0. When we're factoring, the quadratic always has to be equal to 0. So let's say 0 equals x squared plus 3x plus 2. Let's get rid of this one for now. And we are asked to factor it. The first thing you want to do when you're asked to factor something is there a number in front of the x squared? Is there anything in front of the x squared? This includes just a negative. We can get more on that in a second. So just, is there a negative in front of it? Is there a 2, a 5, a 10 million? Is there anything in front of the x squared? Here there isn't. That makes our job so much easier. So we want to know, when we're trying to factor, it's a puzzle. We want to try to find two numbers that multiply to get this last constant that's by itself, but add to get that middle coefficient, that b. The easiest way to do this is to look at this and say, what are the factors of it? Well, with 2, it's pretty straightforward. It's prime, so it's only 1 times 2. And it could be a -1 times a -2, but we don't have to consider that because this sign in the middle is positive. If this sign were negative, yes, you'd be looking at -1 and -2. But the sign here is positive, so we don't have to worry about those. So 1 times 2, and does 1 add up? And 1 plus 2, does that add up to 3? Yes, it does. So, okay, 1 times 2 is 2, 1 plus 2 is 3. Hey, we've got our factors. Then you put them There we go. Okay, it was a little problem, a little stream of me. Okay, there we go. Got that sorted. Then we're going to put them into two parentheses here. There's going to be an X at each parentheses. And because we have two pluses, and we have these two positives over here, plus and plus. And then we put our 1 and our 2, boom, and we factored it. Why does this matter? Why does the factoring matter? Well, if we factor it, when it's set to 0, we can solve. We can figure out what X is. Excuse me. Like I mentioned at the beginning, I had COVID a few weeks ago, so there's a lingering cough. I can edit it out when I'm recording, but not when I'm live. Right, so x plus 1 times x plus 2 equals 0. These two things multiplied together equal 0. So one of these has to be 0. Has to be. We don't know which one, but one of them has to be 0. We multiply them together to get 0. One of them's got to be 0. So you set each one separately equal to 0, and then you're going to solve. We're going to undo what's been done on both sides. In this case, we're subtracting because things are being added. And we get that x is equal to -1 and x is equal to -2. Boom, -2. Okay, so that's our first level of factoring. What is our second one? Our second one is when we have something like this. Very similar to what I just did, but it has a negative out in front. What do? This is something, it doesn't get covered a lot, I find. A lot of students don't have this covered in class, or the teacher's going a roundabout way. I don't know why. Because there is an unbelievably easy way to do this. All you have to do, this is it, is factor out a -1 out of the whole thing. That's it. Change the sign on everything. And then factor like you were doing before. That's it. And if this is a case where you're setting it equal to 0, you can divide everything at this point by -1, and it gets rid of it entirely. If you're just factoring and there isn't an equal 0, then you have to keep it along for the ride until the end. It has to be part of your final answer. And this is one of those cases where you need to follow your teacher's lead, however your teacher wants you to do this. So if you have this -1, and this is the example we just showed you where you factored it and you get x plus 2 times x plus 1. I just added that extra -1 out there to be the little wrinkle. At this point, it depends on your teacher how you should present it. Or on the SAT, you might have to look at multiple questions to see which one is going to be your right answer. This is absolutely correct as is. Some teachers will want you to distribute the -1 by multiplying it through one of these. Don't do it to both of them. Big no-no. Just pick one. And with the SAT, you might have to look and see, did they multiply -1 by the first one or -1 by the second one? So what that's saying is, if I multiply -1 by this first one, I would get -x minus 2 times x plus 1. And if I chose to multiply it by the second one instead, I would have gotten x plus 2 times -x minus 1. And that's, that depends on your teacher, how they want you to present it. It just is, Me, I like it like this. I think it's clean, simple, easy. The -1's out front. That's it. But, do what your teacher tells you to. Okay, next level up of factoring. So we covered the basic one, the introductory one, the -1 in front. The next one is when we have a coefficient in front of the x. If you've heard me say this before, I apologize. But for anyone who's new, if you have a question or a topic you'd like me to cover, drop it in the comments. Just put question in front of it, and we will absolutely get to it. Okay, so if we put a coefficient in front of that x squared, let's say I had 2x squared plus, let's say, oh goodness, I didn't write one of these down ahead of time. Shame on me. I prepared all this stuff and I didn't write down once I could reverse factor it. Oh, goodness gracious. Okay, let me think for a second. This is so unprofessional. I'll say plus 5x plus 2. I hope I did that right in my head. Okay. Right, so the difference between this one and the original version, the first phase of factoring, when we're saying what multiplies to this one, but multiply and adds to that middle one. Well, we got this 2 out here now. We got a 2. What do we do with it? Here's what you do with it. You multiply these 2 together first. So 2 times 2 is 4. And then we bring that 5 down. And now it's what multiplies to get to 4, but adds to get to 5. Right, so what are our factors of 4? 1 times 4 and 2 times 2. Both multiply together to get 4. Which of these adds to get 5? That would be 1 plus 4. So those are my 2 factors. And you're like, oh, yay. So can I just do like 2x plus 4 times, x plus 2 like that? Because, it's a 4 and a 1. Like, no. We can't do that. There's another step. Because of course there is, right? Of course. These are not like in the first form of factoring where we can just stick them in binomials with an x. We have to go to another step called grouping. And it's not that grouping is it's not a hard mathematical process to do, but a lot of times it doesn't make sense to students what's going on. So I'm going to show you that, tell you what's actually happening, why it works. Okay, so what you do is you're going to split that middle term into these 2 coefficients. So 2x squared plus 1x plus 4x plus 2. Okay, and then you're going to group by putting the first 2 together and the last 2 together. And no, it does not matter if you had reversed these. You will get the exact same answer, I promise. Either way, you're going to get the same answer. Right. And you're going to look for a greatest common factor in each group. And what's left behind, if we've done our job right, will be the same in both groups. That's sort of the telltale, we done messed up, is you need to go back and redo stuff, is if when we pull out the greatest common factor, the 2 binomials are not the same. So for the first one, we got 2x squared plus x. There's no coefficient there, but there is a variable that's in both, x. So I can pull out an x and leaves behind 2x plus 1. And then on this side, 4x plus 2. There's not a shared x, but there is a shared coefficient. I can pull out a 2. And leaves behind 2x plus 1. Hey, they're the same, which is what we want. Then we did our job right. Now here's the tricky part that causes a lot of confusion, and I totally get why. Teachers will then say, okay, so now you can put x plus 2 times 2x plus 1. And most of the students go, what? Why are you doing that? What is happening? Why is the 2 coming away and then there's a 2x plus 1? If we use some real numbers in here, I think it makes it a little clearer. So let's say I had x times y plus 2 times y. I said real numbers. I'm putting a variable in place of the 2x plus 1. All right, so x times y plus 2 times y. Right? You know what? I'm rethinking this as I'm doing it. Let's do it even a little different. Let me show you a little different way. Okay. Use all numbers, no variables. All right, so let's say I had 5 times 3 plus 2 times 3. Okay? 5 times 3 plus 2 times 3. I have 5 3s and I have 2 3s. So altogether I have 7 3s, right? It's the same principle that we use when we say 5x plus 2x is 7x. Okay? 5 x's, 2 x's, I have 7 x's. So what did I do? I said 5 3s plus 2 3s, or 5 plus 2 3s. That's what's happening here. That's why this works. because we have x, 2x plus 1s, and then we have 2x plus 1s. So when I combine them together, I have x plus 2x plus 1s. That's what's happening when we're grouping. That's why it works. And then if this is set equal to 0, we're right back to where we were for that first type of factoring. You can set each one separately equal to 0. We can solve for x, and we got our answers. Woohoo! Right, but what happens? What happens when you're asked to solve and you cannot factor? It just can't be done. What do you do then? Then we pull out the bad boy, the quadratic formula. It's so helpful, but I totally get why most people don't like it, because it is complex. It can be difficult to remember it. Here it is. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, that's a lot. And just like I mentioned before, this is going back to that ax squared plus bx plus c, that sort of standard form of a parabola. So when we say a, we mean the coefficient of the x squared, b is the coefficient of the x, and c is that little, the constant that's out hanging out by itself. It's too cool for the x's. It doesn't need to be. It's like, no, I just hang out by myself because I'm cool like that. And we put them into this quadratic formula, and we can solve for x, assuming that this is equal to 0. It's got to be like that. Got to be equal to 0, and then we can solve for x. Okay. So let's put one in here that looks a little like it might not have a nice, say 5x squared minus 2x, say plus 4 equals 0. Actually, I'm gonna change this to a negative here. That's gonna make a difference in a minute. Okay. And like, oh, I don't know if this is gonna factor. I try to do some factoring stuff. I'm like, I don't think this is gonna factor. How do I solve this quadratic formula? And also assuming we're not allowed to graph, and quadratic formula is our friend. Okay, so first off, when it says negative b, this means the opposite of b. The opposite. So the opposite of this negative 2 is a positive 2. Then our b squared, negative 2 squared is 4. Negative 2 times negative 2 is 4. And then minus 4 times a times c. 4 times 5 times negative 4. All over 2 times a, and my a is 5, so 2 times 5, which is 10. Okay. Like, okay, did I get all that right? Let's make sure we've done our math correctly. 2 plus or minus square root of 4 minus 4 times 5 is 20. 20 times negative 4 is negative 80, all over 10. So 2 plus or minus 4 minus a negative 80 is 4 plus a positive 80. So 84, all over 10. And then the last thing we have to do is say, can this be simplified? Can we simplify square root of 84? Never assume that it's the simplest form. Always look for those that you can simplify those radicals. All right, so 84, simplifying the radical. 4 is the most common one, and it looks like 4 would go right into that, so that's a good place to start. I go, okay, 4 times 21, and I don't think of any squares that go into 21. 21 is 3 times 7. Nope, there's no squares. That's it. But 4 is a square. Anytime we have a radical, like square root of 84, and say it's the square root of 4 times 21, you can split it up. Square root of 4 times square root of 21. And then we can, simplify that. So square root of 4 is 2. And the square root of 21 just stays there. And then we got that 2 plus or minus and all over 10. And now, home stretch, we can say, is there any number that goes into all of these? That goes into the 2, little 2 that's sitting out here by itself, and the 10? Yes, there is. 2 goes into all of those. It goes into this 1 time. Goes into that 2 1 time. Goes into 5. It goes into 10 5 times. So I am left with 1 plus or minus, I don't have to write the 1 out front, square root of 21 all over 5. And that is my solution for x. Now, if you graph this, you absolutely can find the answer in decimal form if you graph it. When you're graphing a parabola and you're trying to figure out, it's going to be wherever it crosses the x-axis. Ah, what happened there? Goodness gracious. A random text block out of nowhere. All right. So it's wherever it crosses the x-axis is going to be your solutions. However, as you can see here, if I was to zoom in, I go to Desmos and I go, okay, what's my solution? And I know this is not, where they're going to show up. I'm just doing a quick sketch for visualization's sake. That decimal that I see, I'm not going to know it's 1 plus square root of 21 over 5. I'll just have the decimal. And that is the surefire way that the teacher can catch you if she told you not to use your calculator for this. Yeah. Because, calculators are great, but I haven't seen one yet that would do that. I mean, if you've got one, that's awesome. I want to know about it. It would give you that. Just from the graph, it would tell you that this decimal is equal to 1 plus or minus the square root of 21 over 5. But odds are, if she wants the precise answer, she or he, whatever your math teacher may be, they want we'll use the all-inclusive they when we don't know what someone is, a he or she, or what they prefer. The plural form of the singular, I think is what they call it. I'm blanking on that. I digress. Yeah, it's like when you say, a person came to my door. They wanted this. That the plural singular. Yeah. Whatever your teacher wants is the point. Then we just want 1 plus or minus square root of 21 over 5 is most likely what they're going to ask for. All right. Okay, I'm going to move on to the next section. But if anybody has anything they'd like me to cover, put it in the comments and I will cover that instead. Oh, the patterns that are so common and are so easy to forget. Difference of squares, perfect squares, completing the square, and sum and difference of cubes. Okay, patterns first. Difference of squares. This one, oh my goodness. It shows up all the time, and I can't tell you how common it is for students to forget this one. But it's a common one. It's an important one. Anytime you are asked to factor and you see just two lonesome little terms like 4x squared minus 9, and you're like, wait a minute. She just said when we are factoring that we're supposed to add to multiply to the last one, but then add to the middle one, but there is no middle one. What do I do? Anytime you see this where it's just two terms, first thing you want to think of besides greatest common factor is difference of squares or difference of cubes. It's so common. It's so common. And a lot of times we don't use it as much, so our mind doesn't go there, but it shows up. And if you know it, boom, you're going to get this. You're going to move right on. Okay. So this case, it is a square. So we're going to look for a difference of squares. If this had been a cube, we'd be looking for difference of cubes, or we'd be looking for a greatest common factor. Here, there's no greatest common factor. It is a square. Is it a difference of squares? Is this coefficient out here a perfect square? Yes, it is. What is the square root of 4? A 2. X squared. Is that a perfect square? Yes, it is. What is its square root? X. Right. We got a 9. Is this a perfect square? Yes, it is. What's the square root of 9? A 3. So to factor it, all you have to do is write them twice. Plus, minus, factored, done. There you go. I mean, how easy is that? I love that so much because so much factoring is a lot of grouping and all that sort of stuff. And this one, you're just like, boom, done. Oh, I see. someone requesting matrices. Oh, they're my nemesis too. Oh my goodness. I feel you, man. I feel you. Okay. All right, we're going to put a pin in this one, and I will come back and do some of those other patterns in a minute, but matrices has been requested. So, all right, so I'm going to ask, is this specifically like adding, subtracting, multiplying, scaling, all of the above? Right, I'm going to start with the matrices are one of those things that they start and they lull you into this false sense of security because you're like, oh, I got this. And then they like throw multiplication at you and they're like, ha. And you're like, what on earth is happening? So, right. If we have two matrices and we want to add or subtract them, I'm just going to do a basic, like a 2 by 2 here. If we are wanting to add them, all you do is you add the points that correspond. It's the easiest way to say it. So upper left, same row, same column. You add them together. 1 plus 0 is 1. Then upper right, same row, same column in both of these matrices. 3 and 3 is 6. On the bottom, 4 and 5. 4 plus 5 is 9. -1 and 9. -1 plus 9 is -8. That's it. Same if you're subtracting. You just subtract each point all the way along. It's okay. So far, so good, right? Right. Okay. Then we have, we're saying if you're wanting to multiply a matrix by a matrix. We're not getting there yet. We will. We're going to scale up by multiplying by, let's say, a number. Oh, so you meant vectors. Oh, goodness. Okay. Well, I'm going to finish this one of scaling with matrices. Okay. So if you're scaling up, all you need to do is you multiply the 3 by each number in the matrix. So in this case, that would be 3 times 1 is 3, 3 times 3 is 9, 3 times 4 is 12, and 3 times -1 is -3. And that's when we're scaling up. Okay, so saying you meant vectors. Is there a specific vector-related question that you have? Because, not gonna lie, it's been a minute. So let me let me see here. Is there a specific thing you'd like to see covered? A specific question, maybe? Parallelograms. Okay. Okay, let's see. Talking about, oh my goodness. Let me see here. Again, because I'm not going to give you false information, and it has been a minute since I've helped anybody with vectors, so it's like I'm rusty on that one myself. I'll admit it. Let's see. Okay, let me look up, make sure. And this is riveting watching me look up something. Like, how exciting is that? You know what? This is something that I don't feel comfortable, hopping on right now. What I can do, if you'd like, if this would be helpful, this is something I can kind of bump to the top of the line and maybe see if I can get like a video for you next week that's dedicated to it, because again, it's been a minute since I've done it and I do not want to give you false information. So I can do that. But I feel like if I were to just jump back into this when it's been a while since I've covered vectors or talked someone through vectors, and I don't want to give you bad information. I'm sorry. Because a lot is up in my brain, but it's not everything. I'll admit it. It's not infinite knowledge up there. Okay. Okay. All right. I'm sorry about that. Okay, one I want to put in here because it's one of those things that pops up a lot, and I think a lot of students memorize it for a test and then they forget about it and they think, oh, I'm done with that. It's never going to come back again. Is completing the square. And it comes back all the time. It's one of those things. Completing the square is when we are asked to, let's say if we had x squared plus 6x plus 11 equals 0. And this isn't something that we can factor. And as soon as we learn the quadratic formula, that's where most of us go. It's like, well, why would I learn how to complete the square? I'm just going to use quadratic formula. There's no point. Well, it comes back. It comes back in other things. It comes back when we're dealing with circles. It just keeps rearing its ugly head. It's good to know. When we complete the square, you separate this first part from the rest of it. We're going to make an actual physical space. So there's our first one. Actual little physical space. And if you want to, you can go ahead and, move this 11 over to the other side. You absolutely can do that. In fact, I'd recommend it. We'll just do that. Go ahead and we're going to subtract 11 from both sides. We're going to get that 11 over there. Yeah, let's do that. So then we have x squared plus 6x, leave my little gap, and I have my negative 11 on the right-hand side. To complete the square, this all goes back to the perfect square where we have, if I had x, let's use a and b. If I had a plus b squared, and I was to do my FOIL, multiply all that out, I would get a squared plus 2ab plus b squared. It's that sort of principle that we're kind of reverse engineering, wanting to create a series of terms here that fits this pattern so I could rewrite it as a perfect square. That's the idea. And again, because we're talking about cramming for a test or for the SAT or something, I'm just going to tell you the rule that you need, more so than the full explanation of why it works. I have videos on that. You can absolutely watch that if that's what you're wanting to know. The process is you take this middle term, you divide it by 2, and then you take that number and you square it. And that's it. So 6 divided by 2 is 3. 3 squared is 9. And when you add that 9, you add it to both sides. And that little 3 right there, remember that, because now that is the b term in our perfect square. X plus 3 squared equals, on the other side, negative 11 plus 9 is negative 2. That process, completing the square, if you are dealing with circles, to a lesser extent ellipses, there's things like that. It comes up in other areas as well. It's just so common. It just really is. And we all tend to forget about it when we're dealing. As soon as we finish that, like, I'm done with completing the square. I'm not doing that again. Oh, good riddance, completing the square. And then it comes back again, and I'm sorry. But yeah, it's a good one to know. The one sort of thing to remember with this, it's really important, is before this step right here where you divide by 2 and then you square it, make sure there's nothing in front of the x squared. Nothing. Anything that's there, a -1, a 5, a 6/7, I don't care, whatever it is, you have to get rid of it. You have to divide everything by that coefficient before you can move forward. Is that going to make the next step harder and get a bunch of little fractions that are going to make your life miserable? Yeah, Yep, it will. But, you know, that is part of it. That is it. And as we see right here, this leads me into my next topic. Unless anyone has something else they'd like me to cover, I said, if you have something you'd like me to look into, I'm all ears. Put a comment, put it in the comments, and I will cover it if I can. But the next step here would be if I were to solve this, how can I solve this? X plus 3 squared equals -2. Like, okay, I'll take the square root of both sides. Oh, but we got that negative under there. Can we take a square root of a -2? Isn't that impossible? Well, kind of. It's imaginary. So now I would have x plus 3 equals the square root of -2. And this is where our imaginary number comes in, the lovely I, which is equal to the square root of -1. So we want to split this square root of -2, split it up. So in this case, it would be the square root of -1 times 2, or square root of -1 times square root of 2. And that square root of -1 is I. So then x plus 3 would be equal to I times the square root of 2. I have seen some people that put the I afterwards. I don't really care for that myself because I think it makes it look like the I is under the square root. And then we want to get rid of that positive 3. We want to subtract 3 from both sides, and we get that x is equal to -3. And because it is a square root, we're going to say plus or minus I square root of 2. Now, I behaves in interesting ways. I is, come on. I repeats itself. When we talk about I, and we say I square root of -1, you have I, you have I squared, you have I cubed, you have I to the 4th, and then it repeats. And it's the same thing over and over and over and over again. So it starts with square root of -1. Okay, I squared is square root of -1 times square root of -1, just -1. So yes, an imaginary number times itself is equal to a real number. Math. -1. Then we have I cubed. So that is I squared, which is -1, times I again, which is square root of -1. So it's negative square root of -1. Or we can say negative I. And then I to the 4th, you could say is I squared times I squared. So -1 times -1, which is a positive 1. I's are crazy. So, and then it just repeats, because then I to the 5th is going to be 1 times square root of -1. So if you're asked for what is I to a power, you divide it by 4 and then get the remainder, and the remainder tells you which of these 4 it's going to be. And it just repeats over and over and over forever. Okay, so we're a little over an hour into this. I need to take a little pause. If we could, just a couple minute pause here. And let me stop sharing here. So just give my voice a little break, drink some tea, get a really good tea to refresh my voice, and we'll come right back on. If you have any questions in the meantime, pop them in there and I'll cover them when I get back. Let me put something up here so anyone who pops on doesn't, wonder why I've paused for a minute. Okay, so I will be right back. Just give me a couple of minutes and we'll hop right back on with your questions. All right, there we go. Let's get rid of that music. Okay. All right, so I see your request there for simultaneous equations. All right, yeah. Chug me some tea, got another glass of tea, so I should be all set. Go for the next hour here. Okay. Yeah, simultaneous equations, also known depending on your school as a system of equations. There's multiple ways that we can solve these. Let me bring my little, there we go. Bring that up here. Okay. The major ways that we can solve a system of equations is it's either substitution, nobody's favorite, but someone's favorite, I haven't met them, elimination, and graphing. I think graphing is most people's favorites because they're just like, hey, I pop them in the graphing calculator, system of equations where they cross. That's my answer. Done. But yeah, you know how it is. A lot of times in math classes, we have to show our work. We have to do the method is the point. Right. So substitution, elimination, and graphing. Like I said, graphing is the sort of the easy one here. I don't know why it's not letting me move. Paste succeeded. Thanks, whiteboard. Great time to start messing up. Graphing is just where the equations intersect. So for example, let's see, I have a system of equations. Here we go. I have 3x plus 2y equals 13, and x minus 2y equals 3. We absolutely can type those into a graphing calculator, see where those two lines cross, and that's our answer. And we say an answer, it's only one because these are both lines. It's only going to cross once. If they cross, then there'll be that one solution. Excuse me. Sorry, a little frog in my throat there. Yeah. And that point of intersection, that's our answer. It's the only x and y that make that true. Now, if we're talking lines, this is an important little caveat, system of equations, because teachers will throw in those little, those exceptions in there. If I have two lines, there are only three things that can be happening. That's it. There's only three options. They can be crossing at one point, in which case there is one solution, an x and a y. They can be parallel, in which case there are no solutions. They never cross. There are no x's and y's that make them all true. Or it can be the same line on top of itself. They are the same line, infinite solutions. So if you'd like me to go into when we're talking about recognizing the parallel and same line situations, I can. But first I want to focus on solving when it's an intersection, because that's often the most common one is when we solve for an intersection. All right, so assuming that we're not allowed to graph and that we have to solve using substitution or elimination, a lot of times they will specify which one you have to use because like I said, no one likes substitution. I don't know anybody that does. But we have to know how to do it a lot of times for our tests. First one, elimination. I actually like elimination a lot of the time. Elimination happens when we add the two equations together and one of the variables disappears, cancels out. That's what we want to have happen. It needs to happen. So then we only have one variable and that we can solve for. So in this case, here, if we're adding together, you have 3x plus x is 4x. And then positive 2y and negative 2y. Hey, they cancel out. Perfect. It's gone. And then 13 plus 3 is 16. Okay. Now I have just one variable and one variable I can solve. With two variables, not so much. So 4x now equals 16. 4 times x equals 16. need to divide by 4 on both sides because we're undoing that multiplication. I have x on the left and 16 divided by 4, or 4. That's it. X is 4. Then we can plug that back into either one of these equations. It doesn't matter which one, and solve for y. I'm going to do the one that has, come on, undo what I just did. Oh, the whiteboard's being persnickety. There you go. All right, so I'm going to plug it into this bottom one. X minus 2y equals 3. So I plug in 4 for x. And now I've only got one variable again. That's perfect. I'm going to add 4 to both sides. So on the left, I get that, excuse me, subtract 4. I'm so sorry. I'm sorry. I plead distraction. My cat just came in and is like trying to beg for food. Minus 4 from both sides. Minus 4 from both sides. Get rid of that positive 4. So a negative 2y on the left. 3 minus 4 is negative 1. And if we divide both sides by negative 2 to get rid of that, I'm running out of room as always. Then I get that y is equal to negative 1 or negative 2 or a positive 1/2. Now I know that x is 4 and y is 1/2. And we go, okay, cool beans, there's my answer. Now, if we had graphed this, would we have seen that? Oh, yeah. Yeah. Now, what would happen if it didn't cancel out like that, but we were still being told to use elimination? Then we have to multiply by something or divide by something. Multiplication is generally better. I'm not a big divider person. I like multiplying. We would need to multiply by something to make it work. And let's say if we modified this slightly, and let's say this was 2x and 4y. This was what we've been presented with. I'm going to make it almost identical. Make it identical. So 2x minus 4y equals 6. And we were told to use elimination. Nothing's going to cancel, right? If I add these together, I'm going to get 5x minus 2y. I don't have a canceled out variable, so that's no good. What you do in that case is you take one or both, sometimes you got to do both, one or both of the equations and multiply it by a number so that you do have a variable that cancels out. Does it matter which one you cancel? Not in the slightest. Not at all. You can do whatever you want. If you wanted to multiply this whole thing by a positive 2 and this whole thing by a negative 3 so that these were 6 and negative 6 and canceled out, you could do that. You absolutely could. I tend to prefer doing where you don't have to do as much work. So I would look at these two and try to get them to cancel out. So you have positive 2 and negative 4. I go, hey, if I multiply all of this by 2, then this will be a positive 4 here, and these will cancel out. So, okay. So I multiply everything here by 2, and I'm going to write it down here just to make it all compact. So 2 times 3x is 6x. 2 times 2y is positive 4y. And 2 times 13 is 26. And then I can add those two together. 2x plus 6x is 8x. There my y's cancel out. And 6 plus 23 is 29. And then you keep solving like we did before. So anyways, that's the little wrinkle that sometimes happens with elimination. On to substitution. Oh, substitution. It's just, it's not a fun thing. All right, here's, I'm going to give you this good substitution one. Make one that's a little more. All right, so for substitution, let's see, we have x equals y plus 2 and 3x plus 4y equals 48. Okay. Now, to be clear, what I've just provided you right here is not usually what teachers will do when they say they want substitution. They're usually not this nice. They don't give you an isolated variable. And when I say an isolated variable, I mean one variable equals yada, yada, yada. And that's what you want when you're doing substitution for a system of equations. You want either x equals or y equals. So then you can very easily say, if x equals y plus 2, I go to my other equation, and everywhere there's an x, I insert a y plus 2. And that's how you would solve it. If you are presented with a system of equations and you are told you have to use substitution, and that happens, in math classes, we have to do what our teacher tells us to do. If we're told you have to use substitution, and it's not like this, it's not isolated, you have to isolate it yourself. So like say if it had been x minus y equals 2, you would need to either isolate the x or the y and then go to the next step, which we're about to do. A lot of times with the SAT, they will actually do that. Well, they'll do it like this. They're nicer. I don't know why. PSAT as well. Right. So as I said, once we have this isolated, that x is equal to y plus 2, I'm going to find an x, wherever there's an x in the other equation, and plug in that y plus 2. So 3 times y plus 2 plus 4y equals 48. And I distribute 3 times y and 3 times 2, 3y plus 6 plus 4y equals 48. Combine my like terms. 3y plus 4y is 7y plus 6 equals 48. I'm going to undo what's been done there. Subtract 6 from both sides. I get 7y equals 42. Okay, now I need to undo what's been done again. It's being multiplied by 7, so I divide both sides by 7. And I get y equals 42 divided by 7, or 6. And just like with the other one, excuse me, I can plug it into either of these. I pick the one on top. X equals y plus 2. So x equals 6 plus 2. I plug that 6 in there. 6 plus 2 is 8. So x equals 8. 6 and 8 are my solutions. Okay, it says, hi, does elimination method only work when your x or y cancels out to be 0? Let's see there. Yes, it only works when the x or y cancels out to be 0. Absolutely. The reason why is if it doesn't, you're still left with 2 variables. So like, let's say if I had, oh, Hibiki. Knock my notes over, silly kitty. So if I had 3x plus 4y, my y's look like x's, 4y equals 3, and I had 2x minus, 2y equals 7. I go, okay, I'm going to do elimination method. I'm going to add them up. What happens if I eliminate them without making sure that something equals 0? 3x plus 2x is 5x. 4y and negative 4y is positive 2y, and 3 plus 7 is 10. I can't do anything with that, unfortunately. You have to have it down to 1 variable. If you are having a standalone equation just by itself, and we're just looking at that one equation, I cannot solve for x or y because I have those 2 variables there. It must have only 1 variable for me to solve it when I'm just looking at it. And so, okay, 5x plus 2y equals 10. Like, there's no way to get an absolute solution for that because I could plug any number for x and get a value for y. If I plug in a 1 for x, I can get, that y is 0. If I plug in 0 for x, I get that y is 5. I cannot find a single solution for this. So to find a single solution, it has to have only the x or only a y. That's it, just 1 variable. So for that to happen, I have to eliminate something. I have to get rid of something. So like for this one, I would go, okay, these are pretty close to canceling. If I multiply all of this by 2, I've got my same first equation. Then I've got 2 times 2x is 4x, 2 times negative 2y is negative 4y, and 2 times 7 is 14. And I go, okay, now when I add everything together, 3x and 4x is 7x. The y's cancel out. They're gone. And then I get 3 plus 14 is 17. And then there you go. Now I have just an x. Boom. I can solve for that. I can definitively. So I hope that makes sense there, that you have to eliminate things. Something has to be eliminated, has to disappear. Poof. Okay. So we're saying for use substitution for this particular problem, we're saying, or for, we like me to go through substitution again. X. An appropriate moniker for today's one. So anytime we're using substitution, we always have to have an isolated. We either have to have an x equals or a y equals. We may be given that. We may not. It depends on, what our teacher is. So, okay, so they're from X. We're saying substitution. Just asking a little clarification there. Would you like me to go over substitution again? Do you have a question about substitution? Please let me know. Okay. Something that, let me get a sample problem for this. This is sort of the big epic one, is when you have, you guys want to see this, I'm happy to do this. It's going to take a little minute to do it, is when you have 3 variables. Have you guys had to do this, where you have to do this kind of thing, elimination of system of equations, but there's 3 variables? Okay, good. X saying got it. All right, good. Okay. Yeah. Say yay or nay. Would you like me to go over the 3 3 variables? If so, I have to get a sample, an example of that one. System of equations with 3 variables. That is when you have an x, a y, and a z. Let me see, like a sample problem there that I can show you. Okay, your practice problem. Okay, so this would be things like, I'm pulling from a website. They have a practice problem there that I can pull from. Thank you, Lamar EDU. So here's an example, like say 2x plus 5y plus 2z equals negative 38. 3x minus 2y plus 4z equals 17. And then negative 6 plus y minus, oh, my handwriting is getting so bad. I'm sorry about that. Minus 7z equals negative 12. Okay. This kind of problem, what you do for this is one of those, it's methodical, it's long, but you got to be careful what you're doing. You have to do the same sort of elimination substitution, but you have to do it multiple times and be very methodical in what you do and very careful. If you're presented with a system of equations that has 3 variables, you're going to pick any 2. You're going to do 2 different pairs, and they have to be different. But you're going to pick 2 of these equations, put them together, eliminate something. Take another 2, any 2, put them together, eliminate something. All right. So when we look at this, I'm looking for things that could be easily eliminated. And I go, okay, if I put these 2 together, I can multiply all of this by 2, and then those will cancel out because that'll be a positive 6x and a negative 6x. All right, so that's my first pair. Then these 2, I can go together. I multiply all on top by a negative 2, and then this will be a negative 4, and then these will cancel out. And you go, okay, I think that's good. Ah, but is it? No. It's like, you don't want to get sucked into that. Because what you want to have happen is you want to have the same thing cancel out both times. This is the part that trips people up. The same one has to be canceled in both of them. So I am going to try to cancel out the x's, get rid of the x's so I only have y's and z's. All right, this is going to stick with me on this one. It's going to take a minute. All right, so our first pair, I'm going to write it down here. I'm going to put it in green. 2x plus 5y plus 2z equals negative 38. Then 3x minus 2y plus 4z equals 17. And this other one I'm going to put in red. 3x minus 2y plus 4z equals 17. Then negative 6x, that third one, plus y minus 7z equals negative 12. All right, and I want the x's to cancel out of both. Now, the one on the right is going to be easier. The x's are going to cancel out of that one pretty simply. If I multiply everything here by 2, and I'm going to write it right beneath it, kind of keep it condensed on this one screen. So I multiply everything here by 2. 2 times 3x is positive 6x. 2 times negative 2y is negative 4y. And then 2 times 4z is positive 8z. And then 2 times 17 is positive 34. In the interest of keeping it clean, I'm erasing that. Okay, so there's my two new sloppily written equations. Over on the right, on the right side, I can add those together now. I didn't change my stylus to an eraser. I can add those together. And the x's cancel out. They are eliminated. Thank goodness. X's are gone. Y plus negative 4y is negative 3y. Negative 7z plus 8z is a positive z. And negative 12 plus 34 is 22. Okay, back on the left. I need to do it to both of them. Both of them have to be multiplied in order to make this work. All right, so I'm going to multiply everything on top by a negative 3 and everything on bottom by a 2. So I will get a negative 6x and a positive 6x, and those x's will cancel out. All right, so first one, negative 3 times 2x, negative 6x. I probably should be writing that in green. Yeah, negative 6x. Then negative 3 times 5y is negative green, negative 15y. Negative 3 times 2z is negative 6z. And then negative 3 times negative 38 is positive 108. Yeah, double checking that in my head. Positive 108. Okay, there's the first one done. I am so praying I don't make a mistake in this. As you can see, there's so much you have to do with these. It's so easy to make a mistake. All right, 2 times 3x is 6x. 2 times negative 2y is negative 4y. 2 times, wrote that in blue, 2 times 4z is positive 8z. And 2 times 17 is positive 34. Okay. Then when we add these together, the x's cancel out. Yes. Negative 15y and negative 4y is negative 19y. Negative 6z, and I can't read my own handwriting, I'm so sorry. Negative 6z plus 8z is positive 2z. And 108 and 34 is 142. Oh, Lordy, am I hoping I didn't make a mistake in there, somewhere in there. Okay, so now all of that was just to get to where we have two equations that we now can do elimination again. Again, I know. So negative 19y plus 2z equals 142. I'm just rewriting them from down below. And negative 3y plus z equals 22. The easiest way I see forward is adding those together. And the question I see popping up, is this non-calculator? Yeah, I am covering non-calculator just because I know depending on your exam on the SAT, you're allowed a calculator, but some students, if you have a test and exam, some may not be allowed a calculator, so I like to do both ways. All right. So Okay, the easiest way I can see forward is to eliminate the z's because I've got this z and a 2z. And all right, so I'm going to multiply everything on the bottom by a -2. And okay, so if I multiply all this by -2, that -6y, negative, oh, stop. Why is this not working? Okay, there we go. -3y. I'm getting punchy, y'all. That's not good. -3y times 2 is -6y. And I just realized, I'm so sorry. That was supposed to be times a -2. I am getting punchy. All right, get it together, Alyssa. Get it together. -3y times -2 is a +6. Positive z times -2 is -2z. And 22 times -2 is -44. And I have a little visitor here who just got in my lap. So say hi. That's Dita. All right. Okay. So we add those together. -19y and 6y is -13y. The z's cancel out. And 142 minus 44 is 98. And oh my goodness, am I hoping? I don't think I did it right. Oh my goodness gracious. I'm going to be so embarrassed if I didn't do that correctly. Oh my goodness gracious. Did I make a mistake somewhere? Oh, I'd be so embarrassed if I did. I did make a mistake somewhere. I'm so sorry. I was so afraid this was going to happen. I was so afraid it was. I was like, it's so easy to do with these. Okay. I own up to it. No one's perfect. No one is perfect. I will say the process that I showed you is correct. I clearly made a mistake multiplying somewhere along the way, and I'm sorry about that. I am. Dang it. And at this point, it's hard to find out. Okay, the process absolutely is correct. So what happened is, as you get to this point and you've solved for y, then you would use that y, go back into one of these two equations, solve for z. You can plug it in for in either one, and you solve for z. Now you have a y and a z. Then you go back, pick any one of these three equations, plug in the y and z, and you can solve for x. So again, I did make a mistake somewhere along the way. That's one of the dangers of doing this live. It absolutely can happen. And when you got this much stuff going on, and it's not popping out at me where I messed up, and I'm sorry about that. Darn it. But yeah, the process is correct. The process I showed you there is right. I'm gonna rewatch the replay of this later and be like, oh, there it is. That's where I made that mistake. Darn it. Happens to the best of us. But yeah, you're wanting to you pick two of those. It's the process again. You're going to pick any pair of two. It can be those two. It could be those two, those two. Pick two pairs. Set them up so that you eliminate the same variable in both of them. That gets you to the point where you have a more familiar system of equations with just two variables. Use either substitution, elimination. You can use graphing if you're allowed to solve for those. And then you've got those two variables, and you can find the third. So again, I'm kicking myself for that. I just am. It happens, but yeah, see, that's my fault for not preparing that one ahead of time. That was a shame. Shame on me. Shame on me. Okay, let's see. All right. Again, if anyone has anything they want to cover, pop it in. I'm going to talk a bit about functions. Functions are one of those things. They show up constantly. And my goodness, they show up all the time on the SAT and the PSAT. Functions all the time. Ooh, still hot. Nice. And if you're like me, the first time you heard about a function, you were like, what is the point of this? Because we have, let's say, f of x equals x plus 3. And they're like, we're not going to call it y equals x plus 3 anymore. We're going to call it f of x. And you go, what is the point of that? Why? Why is this better? It isn't. It is a little different. here's the difference. When we have y equals x plus 3, which is, the way we usually graph things, it doesn't really matter. We can plug in a y and solve for x. We can plug in an x and solve for a y, and they're sort of viewed the same way. They don't really have this sort of difference. But with a function, it is very much about an input and an output. It's very specific. What's over here, and the variable that's listed in the middle, and the f of whatever it is, it could be something else. It's generally x. That is our input. And the output is the f of x. So the number goes in. What do we get? Very distinct input and output. When you're asked to evaluate a function, like let's say if f of x equals x plus 3, and I was asked to evaluate what is f of 7, anytime you're given this number, f of a number, they want you to take that number, go into the original equation, and everywhere you see that variable, plug in the 7. In this case, it would just be 7 plus 3. 7 plus 3 is 10. So f of 7 is 10. And it can be, as sort of basic with just a couple terms, or it can be infinitely complex. Functions are of a lot of things. The one thing that you want to say with a function, because we are talking about input and output, for every input, there can only be one output. So if we have a graph and you are asked, is this a function? Let's say if you have like something crazy, it doesn't matter what it is. The one surefire way to see if it's a function, if you're just looking at it, is the vertical line test. So you take a ruler, piece of paper, a straight line, whatever, and you drag it along, and I'm just looking at the right edge here of this ruler. And if you drag it along, is there ever a place where it crosses the line more than once? If the answer is no, it's a function. It doesn't have to be, doesn't even have to be in one piece. You can have, functions like this, like piecewise functions, step functions. But as long as I'm taking that right edge of that ruler and going along and like, nope, there's no place where there's two, or it crosses it twice, it's still a function. So there's a lot of variety in functions. You have like absolute value functions. You can have parabolas. You can have cubics. All of these are functions. One of the other things that happens a lot in the SAT is where they have, I call them nested functions. I know that's not the real name, but that's how I always think of them, is when you're given something like f of x equals x plus 3 and g of x equals the square root of x minus 2. What is f of g of f of g of 12? Zoom out. There we go. It's just a step-by-step methodical process. So here you start at the inside. What is g of 12? You look at g of x. Okay. Everywhere there's an x in this equation on the right, I'm going to insert 12. So g of 12 would be the square root of 12 minus 2, or the square root of 10. All right, so now I know that g of 12 is square root of 10. So now it's what is the f of the square root of 10. All right, I look at my f of x. Wherever there's an x, I plug in square root of 10. So square root of 10 plus 3. I can't really do anything else there. And that is my answer. That f of g of 12, what I started with, is square root of 10 plus 3. And there we go. Again, this type of problem, even if it doesn't show up a lot on any algebra exam you have it coming up, oh my goodness, does it show up on the SAT and the PSAT all the time. Boy, do they love it. They love the f of g of x or h of g. Oh man, they love it. It's one of their favorites. So definitely one to remember if you're getting ready to take if you're going to be taking the SAT or PSAT anytime soon. Definitely. Okay, let's see. Ooh, rational expressions. That's a good one. Okay, rational expressions are when we have variables in a fraction and they're in the denominator. That's the shorthand version. When you got variables They get like binomials and things. Those are our rational expressions. And they love making us add, subtract, not so much multiply and divide, I think because it's easier and they don't want to make your life too easy. They always want to have adding and subtracting rational expressions. And these can get very awkward very quickly. So say something like, 2x over x plus 1 plus, I'll be a little nicer at the beginning, x over x plus 3, something like that. It's really tempting to look at this and go like, okay, well, the denominators need to match because they're fractions, and we need to add, the denominators need to match when we add fractions like, 1/2 plus 1/2. The denominators match, and so we just add the numerators. I'm like, okay. I'm like, all right, well, I've got x plus 1, I've got x plus 3, so I can just like add 2, right? Add 2, top and bottom, and I'm done. Oh, I wish. Nope. Unfortunately, that is not the case. When it is adding or subtracting, we have to keep it as a unit. It cannot be split up. Yeah, I'm sorry. And as the realization dawns, like, what does that mean? Oh, no. Does it mean what I think it means? Oh, yes, it does. It means that you have to multiply this whole thing by whatever's missing. What do I mean when I say what's missing? Here I've got an x plus 1 on the left in the denominator. I have an x plus 3 on the right in the denominator. They both need x plus 1 and x plus 3. So you have to multiply by what's missing over itself. Because when something is over itself, it's equivalent to 1. So we can multiply it by 1, doesn't change nothing. It's fine. So on the left, the x plus 3 is missing. So I multiply by x plus 3 over x plus 3. And I want to keep that blue. Make it blue. 2x over x plus 1. And then on the right, I've got my x over x plus 3, and x plus 1 is missing. So I need to multiply by x plus 1 over x plus 1. And I missed that. Oh, so I missed that 15 minutes ago. X said I'm really fun for math. Oh, thank you, X. I'm sorry I missed your comment there. Thank you. Very kind of you to say. All right. Now, depending on what you're doing, if this is SAT or PSAT, this is the point when I say look at the multiple choice answers that you are given and see if they're wanting you to distribute this or if they're wanting to leave it in x plus 3 times x plus 1. If you are doing an algebra exam or a test, follow the directions, read very carefully what the teacher says, how they want you to be presenting it. Do they want you to combine this, distribute it, or leave it as x plus 3 times x plus 1? For the numerators, you're going to need to distribute it. That's just, yeah. All right, so the first one, 2x times x plus 3, we need to distribute. 2x times x is 2x squared. 2x times 3 is 6x. And then over here on the right, x, I'm going to distribute. X times x is x squared. X times 1 is x. And this is being added, which is nice. Just add. And then all of this is all over my new little denominator of x plus 3 times x plus 1. Because once the denominators match, we can add the numerators and it's all good. Now all we have to do is make sure that we have combined like terms. We've got a 2x squared and an x squared. I can combine those to be a 3x squared. And then 6x plus x is a 7x all over x plus 3 times x plus 1. And like I said, some problems that you do may require you to distribute that using FOIL. Others, they may want you to just leave it as x plus 3 times x plus 1. Just depends. And if you were to subtract this is the only sort of thing. I just lost the tip of my stylus. This is why you always have a backup stylus. My tip just vanished. It fell somewhere. I'm not going to look for it now. Backup stylus to the rescue. All right. Haha. Go to erase and like gouge my screen. All right. So if this had been A minus. This is the one little sort of thing here. If this had been a minus, when you go here to subtract, remember you'd be subtracting the whole thing. That's the catch. That's what gets people sometimes. You'd subtract the whole thing. So it is, and I love changing the signs. It makes it so much easier to me. So I would change this to a plus, and then you change the sign of everything in the parentheses, and now you're good. Now you don't have to worry about the parentheses anymore. So 2x squared plus a negative x squared would be x squared, and a 6x plus a negative x would be 5x. And there's that one. With these kind of things, it does not happen in this particular problem, but this kind of problem, always be aware at the end if there's any greatest common factor or any way you could just factor it using the methods we discussed earlier in this session to see, like in this case, you could factor out an x times x plus 5, because do not put it past your teacher, the SAT, to have something that then you're like, oh, you needed to factor, and then there was something you could cancel on top and bottom. Doesn't happen in this case. You know, x plus 5 does not match either of these on the bottom. But, oh, teachers love doing that, because then you would, put your final answer. Like, say, for example, if this had been an x plus 5, and like if you had given it like this, and they're like, well, you got it wrong because you didn't cancel out the x plus 5. And then you grumble like, I got it wrong. Yeah, I've been there. We've all been there. So frustrating. So always look out for that so you're not in that predicament. Okay, let's see. Equation of a circle. That's one. All right, yeah, if anybody has any questions, I will, do my best to cover whatever topics you want me to cover. So I'm just going down the list in the meantime. All right, equation of a circle. This is one that, oh, does it look fancy? But it's really straightforward, and it shows up on the SAT all the time. Can't even tell you how often it shows up. And it's not included in your list of equations that are provided by the SAT. They don't do it. I think sometimes students think it's going to be there, and then they're like, what? But it's super straightforward. Looks fancy, super straightforward. If you are given this equation, this is the equation for a circle. This is a circle with a center at H, K, and a radius of R. That's it. You take the opposite of the number you see here, the opposite of the number you see there, take the square root of this number, and you've got your center and your radius. Very straightforward. There is one little wrinkle, because of course there is. There's always a wrinkle. So if you were given an equation, let's say x plus 5 squared plus y minus 2 squared equals 36. Say, okay, the opposite of positive 5 is negative 5. The opposite of negative 2 is positive 2. The square root of 36 is 6. So I know this is a circle with a center at negative 5, 2, and a radius of 6. And that's it. The little wrinkle that comes in, and this is the one little wrinkle that everyone hates with circles. You see how this is this nice, pretty x plus 5 squared, y minus 2 squared? Yeah, sometimes they give it to you in formats like, x squared plus 6x plus, y squared equals 36. And then they'd be like, put this in standard form. And you're like, what? And that's where our old friend completing the square comes in. So I said before in the stream, if you have completing the square, you think you don't have to use it. You use it for that one test, and everybody forgets it. Everybody does it. And then it comes back again. This is something that shows up on the SAT. Absolutely. It just does. And they will want you to use completing the square to turn this into a square like that. And you'll have to use your process like in this we did with completing the square earlier, where you divide this by 2, which gives you 3, and then you square it. That's 9. And then again, we have to add it to the other side as well. Yeah. That's one thing, because I did it earlier. I know some people who are on here probably didn't see that earlier. So if you're wanting me to go over completing the square in more detail, again, I'm happy to do that. But yeah, it's that process that we discussed earlier. There it comes up again. It keeps rearing its ugly head, completing the square. And then it's on standard form. Okay. Ellipses. No. Do you guys have covering ellipses? Do you want me to cover that one? Because I can. Ellipses are very similar to circles in they're very similar in their equation. I can do that, but I don't know how common that is. Something I think is a bit more common would probably be our trig functions. So let's see, our sine, cosine, and tangent. Those start popping up a lot of the time. Okay. The way that you can try to remember these is, boom, I wrote it right, SOHCAHTOA. That is what is commonly used. To me, I didn't find this very helpful, frankly. A lot of teachers use it. A lot of teachers present this and go like, oh, and you got it now, like SOHCAHTOA. And I'm like, it's not even a word. How's it supposed to help me? Like, I would get these backwards, realize it's SACO or SOCA. Which one is it? There's two ways you can keep this straight. If you can remember the TOA, O-A, so it's O-A, O-A. SOHCAHTOA. So it's O-A, O-A. Same vowels twice. Another way is it's very similar to the name Pocahontas. It's similar to that name in that you have that O and then the A, and you have that ka right there. So that helped me remember it. It's like, okay, so like in the name Pocahontas, O comes first and then the ka comes second. That helped me. But yeah, they give you this mnemonic and I'm like, how is that a mnemonic? It doesn't really help. So what does it stand for? What does it mean? What is it trying to tell us? If I have a right triangle, and let's say this is going to be angle X, and there's A, B, and C. This stands for the sine is the opposite over the hypotenuse. So the sine of angle X is equal to the length of the opposite side, the side it's looking at, that's the opposite side, over the hypotenuse. The hypotenuse is always the longest side. So it is equal to B over C. Then we have the cosine, the ka part of this, the cosine. So SOHCAHTOA. So the cosine of X is adjacent over hypotenuse. The adjacent is the side that's right next to the X, like bumping elbows with it. It's adjacent to it over the hypotenuse. So A over C. And then the tangent of X is going to be the opposite over the adjacent. So that opposite side, the one it's looking at across the table, over the adjacent side. So that's B over A. Now, this is something where you pretty much have to use your calculator. Some places, they may have like a chart that's very old school, where they have a chart of all the sine, cosine, and tangent, all these trig values. They're just measurements. They're measurements people observed. Now they said, okay, if you got a right angle and you know, a right triangle, excuse me, and you know the angle of this, then the ratio of these sides is always the same. Always. So if we can measure these sides, we can figure out what the ratio is and we can record it. We can use it to reverse engineer and find the lengths of sides in triangles that we don't know. So that's what it is. And this is really one of those things where you need your calculator to either give you the value of the sine of an angle, the cosine, the tangent of the angle, and then you can reverse engineer things. So that's the point of that. Yeah, and so a lot of these will be things like they might tell you what the value of X is, then give you one side and ask you to say, okay, now solve for the other side. So like they say, okay, so X is 30 degrees. And if B is 5, then what is C? What is the hypotenuse? Well, in this case, they're wanting you to kind of key in on, okay, if I know that X is 30, I'm given the opposite side, and I'm trying to solve for the hypotenuse. Which one of these involves opposite and hypotenuse? That's sine. So you plug in 30 for sine, you get sine of 30 using your calculator, or if you're a place that uses the chart still, no problem with that. You know, you can use that chart, get that number, plug in 5 for your B, and then you can solve for C. That's how that works. That's how you're using those. Okay, we are coming up on 2 hours now. I'll admit it, my voice is getting a little raw. But if anybody has any questions, I mean, I covered a lot. It's frankly kind of impossible to cover everything algebra related in 2 hours, but I was trying to give you guys the highlights. If you have anything that you'd like me to cover, as we're kind of winding down here. Let's see, I'm looking over my list. Oh, only one thing I can think of that doesn't get covered often, but is a nice, easy one to kind of have in the back of your head is inverse of a function. Inverse of a function. So if I have something like f of x equals x squared plus 2, and they say, what is the inverse of this function? The only thing you have to do, you replace f of x with y, and then you're going to swap the x and the y. So wherever there's a y, put an x. Wherever there's an x, put a y. So in this case, it would be x equals y squared plus 2. And then you need to get it back into y equals format. So let's see. Okay, so I have I do have a comment here. It says to make x the subject. Make y, make x the subject. Okay, make x the subject. So you're commenting on the inverse, or you're asking me to cover something? Just want to make sure on that. Sorry if I'm misunderstanding. I apologize. So, okay, so for this one, I was saying you want to solve for y. So we want to, here we'd subtract 2 from both sides, and we get that y squared is equal to x minus 2. Oh, no, sorry, saying I thought it was inverse. You're right. It is the inverse. We're taking the inverse. We started with f of x, and we are making the inverse. This is down here. This is going to end up being the inverse. Yes, that is what we're doing. But I find that when you plug in the y for the f of x, it makes the process easier when you're swapping. So sorry about that. I misunderstood you. I apologize. Okay, so y squared equals x minus 2. Take the square root of both sides, and y equals the square root of x minus 2. And you're like, we're looking at this graphically. And again, it's been 2 hours, so if my explanations are not as good as they were earlier, I'm sorry. I apologize. I'm trying. All right, so when you have an inverse, when you look at it graphically, it is going to be reflected across the line of x equals y or y equals x. In most of the cases, it's going to be this perfect, beautiful little reflection. But because this is a function, it's an inverse of a function, you get to this y equals x minus 2. That does not look the same as x equals y squared plus 2 if you plug them both into a graphing calculator. This first one, x squared plus 2, is going to be a parabola, looks something like that. It's moved up 2, kind of like that. Not great, but so you'd expect it to reflect across the y-axis, this y equals x, that it will look something like that. But it doesn't. It's this y equals square root of x minus 2, so it ends up looking just like that. And that's because it's not a function. If we kept it in this state, x equals y squared plus 2, it would be a sideways parabola that looked like that, but that would no longer be a function. It has to be in this square root of x minus 2, so it's only the top part. Because remember that ruler test we talked about? You know, that straight line test going up and down? If we had that y squared plus 2, and we put the ruler up. See, it's crossing it twice, so it's no longer a function. So that's why when we do that, we have that, we get to that square root point. Okay. All right, so yeah, we've just passed 2 hours here. I'm sorry if I'm not as coherent as I was 2 hours ago. I admit it. Yes, I'm flagging a little bit. I'm trying to make sure I'm still saying things clearly, but if I'm not, I'm really sorry. Okay, so I am going to be winding down here, but I'm happy to take any final questions. Anybody has any questions or any last things that they'd like to cover? I'm looking over my list here. Sort of the big things that pop up. Excuse me. Let's see. Yeah, I'm not seeing anything on my list that's really popping out at me as something. Exponent rules, that's something. It's a quadratic complete form. I think that may be a terminology. Let me look. Sometimes there's terminologies differ in different places. Let me look that up real quick and see. Quadratic complete form. About completing the square? Completing the square. Okay. Just to make sure I got that. Okay. Yeah, absolutely. I can go over that one. All right. So completing the square is when we're asked to solve something like this. Say x squared plus 4x plus 7. Actually, I'm going to make it equals 0. Make it equal 0. X squared plus 4x plus 2 minus 7 equals 0. And we're asked to solve using completing the square. We are trying to get to a point where we have something that is in the format x plus or minus a number squared. We're trying to convert this into this. And it's all about the, move this over here so you can really see it. This pattern, if I said that a plus b squared, that is equal to a squared plus 2 times a times b plus b squared. Or that a minus b squared is equal to a squared minus 2ab plus b squared. So we're trying to get this to look like either one of these two so that we can convert it back into a plus b squared or a minus b squared. The first step always is you're going to want to separate this from everything else. So we have x squared plus 4x, and I'm going to add that 7 to both sides. I want to get rid of it. I want to get it away from the x squared plus 4x, I should say. So on the right side, I have 0 plus 7, or just 7. So, okay. Oh, I was saying about 3x squared. Oh, I will get to that in a second. Absolutely. Okay, we're just going to go by stages here. All right, so x squared plus 4x, and we leave this gap. I want to convert this. I want to add something here so that it turns into one of these. Well, there's a plus sign here, so I'm going to go for this one. Now you see here how it says 2 times a times b. This a here, a squared. We always want it to be where it's an x squared. Sometimes we have to do a little change. We'll get to that in a second. But it always has to be at this point a plain x squared. So x will just be my a. Always, that's what we want this to be. So now this here in the middle is 2 times a times b. So it's 2 times my a times my b. And this is going to be b squared. 2 times my a times my b. So 2 times x times what equals 4x. That's the math we're doing in our head. The practical way of looking at this, that's what's happening. But the practical thing is we take this 4, we divide it, by 2. It's because of this 2ab. Divide it by 2. That gives us our b every time. So 4 divided by 2, this is a positive 4. 4 divided by 2 is a positive 2. And now for this number right here, I need it to be b squared. 2 is my b, so 2 squared is positive 4. Well, this is an equation, so I can't just add a number on the left without adding on the right, so I add a 4 on the right as well. So x plus 2 squared, because this is now a perfect square in this format, x plus 2 squared is equal to 7 plus 4, or 11. It's usually at this point that we're asked to solve for x, and we square root both sides. Square root both sides to get rid of that square. And we have x plus 2 equals plus or minus the square root of 11. We want to move that 2 over as well. So it's adding the 2, so we subtract the 2, and we get to our final answer that x is equal to negative 2 plus or minus the square root of 11. So it's getting to the same place as like a quadratic formula, and most students, once they learn quadratic formula, they don't want to do this anymore, and I don't blame them, but it comes back again and again. So it's important to know. So, okay, so you're saying, what if I put a 3x in it? You're saying, how about a 3x in it? Oh, yeah. And that's the one. Let's back it up, back it up. It's so common with these completing the squares where you get weird equations and you get weird things happening. And, you know, it's just, and it's all because of this bit right here where we put a 3 or some other number, any number, in front of the x. If this was a 3, a 4, a -1, a 20, it doesn't matter. If there is any number in front of that x, you got to get rid of it first before you can complete the square. Okay, the first step stays the same. We're going to take that -7. We're going to move it over to the other side. So I'm going to add 7 to both sides. And I get 3x squared plus 4x. And I leave a little gap. On the other side, 0 plus 7 is 7. Okay, so now I must get rid of the 3. So I have to divide everything by 3. Is this going to make nasty fractions that are going to make our lives a little painful? Yes, absolutely. All right, so now I have x squared plus 4/3 x, and then a gap, and it equals 7/3. All right, but I have to follow that same process. I have to follow to get to my a plus b squared. My a has to be x, and I need to get my b by dividing this by 2. So 4/3 divided by 2 is 2/3. So that's my b. And then to fill in this little bit right here, I have to square that. So 2/3 squared is 4/9. I have to add that to both sides. So now I have x plus 2/3 squared equals 7/3 plus 4/9. And if I convert 7/3 into ninths by multiplying it by 3/3, I get 21/9. So if I add 21/9 plus 4/9, I get 25/9. And then I want to take the square root of both sides. And I get x plus 2/3 equals, and you take the square root of this, you can take the square root of the top and the bottom is how you do this. And both of these are perfect squares. I did not plan it that way, and it turned out beautifully. I have no idea how that happened. So the square root of 25 is 5. The square root of 9 is 3. If this had been a perfect square on top, but not on bottom, you would have had to simplify using those radical rules where you have to get rid of the radical in the denominator. That's a different topic. But yes, you would have had to do that, if anyone's wondering. All right, so 5/3. So x plus 2/3 equals 5/3, or plus or minus, I should say, plus or minus 5/3. So now I'm going to subtract 2/3 from both sides, and you get x is equal to negative 2/3 plus or minus 5/3. So if it was negative 2/3 plus 5/3, that would be 3/3 or 1. And then negative 2/3 minus 5/3 would be negative 7/3. Okay. That turned out so much prettier than I expected it to. Okay. Right. You're very welcome. And says, I want to ask the last question. How did you learn math? Any suggestions? A lot of practice, a lot of time. Yeah, I do have an advantage. In that I call it a math brain. It's like where things like I look at math and go, oh, that makes sense. That is not to say that that's necessary to understand math, because it's not, but it does make it easier. So that's a little bit of an unfair advantage, is that, I would look at something and go, oh, okay, that makes sense to me. I get this. But no, it's, you just want the, find somebody. Here's my best advice is find someone who teaches in a way that makes sense to you. That's my best advice for that. Yeah, for that question is, find someone that makes sense. And then you go like, okay, I get it. I get how you're saying it, because different teachers have different styles. And some teachers you're going to look at and go like, I don't have a clue what you're talking about, So do you teach IGCSE? I haven't done that specifically. I haven't done that specifically, but I absolutely could look into that. Definitely. That'd be something I would look into before I could. I've taught a lot of different levels of math. I've tutored children and teenagers and adults. So I've gone from, like elementary math through high school math and even some college math. So I tend to say like, I probably do teach what's in there. I probably have taught the topics that are in there, but I would have to double check and make sure what specifically is covered in that. So I don't want to say, off the top. Much harder than the SATs. I know there's a lot of really difficult tests out there. That's for sure. Yeah. And the SATs has gone through some changes recently, so that it's all levels all in one. Whereas it used to be sort of, they were all hard. Like all the questions were all very hard. And now they have all different levels. So it's more of accurate at gauging where a student is. Because before it was kind of like, oh, you can't do the hard ones. Well, then you're out. Well, someone might, there's a wide range of student ability within there that, even if they can't get those really hard questions. So they've changed that. All right. So yeah, I think I'm winding up here. I'll say complex numbers. Oh, yeah. Do you have a specific question about complex numbers? Wanting to, like the adding, multiplying, things like that? Anything like that you'd like me to cover before I sign off? Biggest thing I think with complex numbers is keeping track of your powers. When you end up with I squareds, I cubes, I to the fourth, because any of those powers, like it changes things. I mentioned this way earlier in the stream. We're talking about imaginary numbers, because you have, and it cycles. So you have I is square root of -1, I squared is -1, I cubed is -I, and then I to the fourth is just 1, and then it starts all over again. So it can be easy to forget that and leave like an I squared or an I cubed or something in your answer, and then that can cause problems. Okay. All right, I'm just gonna leave up here for just a couple more minutes. See if any final questions here. I admit my voice is getting a little sore. My throat's getting sore. So lose it. Okay, I will say I'm gonna put this up on the screen here. let me see. Okay, so yes, I do have, if you are studying for the SAT, if you're studying for algebra, I have a course on factoring and courses on all the math that's required for the SAT over at mathwithalyssa.com. And right now I have a coupon code. It's good until May 16th. And it's EOY 2025. And that's for 30% off any course that's on that site. And it's I also have a site that is a course, that's completely free. That is tips and tricks for the SAT and the PSAT. It's a 10 video course telling you about how to, how to set up a study plan that's right for you, all that good stuff. Also, if you're wanting to book any one-on-one tutoring sessions, here's the site at the moment where you can book me. And I'll have those links in the description below as well. All right, I think we're going to call that. Thank you so much, guys, for stopping by, for asking questions, for commenting. I had fun. I hope you guys had some fun too. Hope that it was helpful. I'm still annoyed at myself about that, whatever mistake it was I made in the 3 variable setup with the X, Y, and Z. I'm absolutely going to go watch that later and try to figure out what I did and then kick myself afterwards. Anyway, so I hope you guys have a great weekend. I will have SAT questions again, those videos going back on Monday. All right, I'll see y'all later. I'm going to wave awkwardly while I hit end stream. Bye.